Okay, today we're going to be talking about section 10-1, and we are simplifying radical expressions. Very first thing we want to discuss are the vocabulary words related to this section, and we're going to start off with radical expression. And a radical expression is just like what you see right here. There's a radical sign that incorporates an expression underneath, and the expression underneath the radical sign is called the radicand. Okay. So one of the rules when you're simplifying radical expressions is called the product property of square roots. And what that states is if you are multiplying together two square roots, you can combine them under one radical sign. Okay, but keep in mind that both the values of a and b, or any value of any variable underneath the radical sign, has to be greater than or equal to 0. Okay, you cannot have any negatives underneath the radical sign, not until later on in your math career. So with that, we're going to start off, we're actually going to start off with just an example. Okay, so our first example is the radical 52. And we're going to simplify this. And the first step in doing this is finding the prime factors of the radicand. Okay, so our radicand is 52, and our objective is to find the prime factors. So I'm going to divide by the first prime factor that I know. We have 2, and this will be 26 left over. Dividing by another 2, I know I can get 13, and 13 I know is a prime number, so I'm going to stop there. Okay, so this means that the value of this radical expression is equal to 2 times 2 times 13. Okay, these are the prime factors. Okay, so when you are simplifying radical expressions, what you're looking for is the pair, because you remember perfect squares, 2 times 2 is 4, so the square root of 4 is 2. So since we have this pair, what we're going to do is we're going to circle that pair. One of them you can cross out, and the other one you will take outside of that radical sign. Okay, so when you go outside, it's going to be multiplied to whatever is left inside the radical sign. In this case, it's the 13. So 13 doesn't have a pair. Okay, the only way you can get out from underneath the radical sign is if you have a twin. Okay, so this is the simplified answer. Okay, let's do another example. Okay, in this example, you have radical 2 times radical 24. Okay, using the product property of square roots, we know that this is equivalent to the square root of 2 times 24. Okay, and 2 is already a prime factor, so I'm just going to break out 24 now. 2 dividing by 2, you get 12. Dividing by 2 again, you get 6. And you can divide by 2 again to get 3. 3 is a prime number, so I'm going to stop here. So the value of 24 is equivalent to 2 times 2 times 2 times 3. Okay, so I'm going to rewrite this. So first I have the 2 here, and now I'm going to put the values for 24, which is 2 times 2 times 2 times 3. Okay, after we do this, what we're doing is looking for our twins. Okay, so looking here, I have 2 times 2, and I have 2 times 2. You can kill off one and set the other free. Kill off one, set the other free. Okay, so outside, what happens when one of the twins is set outside is they will be multiplied. Okay, so that will be multiplied, and this will be multiplied to everything underneath the radical sign, which is just a 3. And 2 times 2 is 4. So 4 radical 3 is our simplified answer. Okay. So let's do one last example just to make sure we understand this concept. Okay, again, we said that when there are numbers outside the radical sign, what's happening is multiplication. Okay, so what we can do is put parentheses around everything. I'm going to use the commutative property now because what we want to do is we're going to focus on everything outside the radical sign. So 7 times 2, okay? And then underneath the radical sign, I can have 30 times 6, okay? Well, I know that the value of 6 is 2 times 3, so let's break out the value of 30, okay? If you don't know it off the top of your head, go ahead and make a factored ladder. This will be 10, 2, and 5. Okay, so 3 times 2 times 5. Okay, so I'm going to replace that with 3 times 2 times 5. Okay, and of course all of this will be multiplied together. Okay, when we simplify, we want to multiply together everything outside the radical sign, 14, and this will be multiplied by everything underneath the radical sign. Okay, and remember, we can use the commutative property because this is all multiplication. I'm going to use the commutative property to put all of my pairs or my twins together. I have the 2 and the 2. I have 2 3s, and then I have a 5. Okay, so what this allows me to do is to clearly spot the twins. Okay, we have our pairs. Cross one out, set the other free. Cross one out, set the other free. And what we have left over will be 14 times 2 times 3, and underneath the radical sign we have just 5. Okay, well 14 times 2 times 3 will give you 84 times the radical 5. Okay, and that's it. Okay, all right, I want you to try this problem here. Okay. The next topic that we want to discuss, it's really important, is when your radical sign or when your radical expression contains variables, okay, because there's a very, very special thing that you need to take care of when you have variables, okay? You want to make sure that the result is not negative, okay? And how are you going to do this? If the exponent inside the radical is even and the resulting simplified exponent is odd, you must use the absolute value sign. Okay? Why is this the case and what does it mean? Okay, so I'm going to use this example of the square root of x squared. Well, we all know that the value of that would be x. But we're going to go back to some definitions, right? We said that in the beginning that the value inside the radical is always positive, okay? But at the same time, the value of x can be positive or negative. So what happens is we have to use the square root symbol, the absolute value symbol. I'll go ahead and label that the absolute value symbol to ensure that this value is positive whenever you have an even exponent and simplify to an odd exponent, okay, because that's x to the first, okay? So just remember, whenever you have an even exponent underneath the radical sign and it simplifies to an odd exponent outside, you're going to have to add in the absolute value bars, okay? All right, so let's use that to do this one example, okay? 45, I'm just going to take a look at the coefficient first. 45 is, let's see, 5 times 9, and 9 is composed of 3 times 3. Okay, so 5 times 3 times 3. Okay, I'm going to first set that up, and I'm going to put the pairs together, because I know I'm going to be using that to simplify. A to the fourth, well, I'm looking for pairs, right? So we're looking for pair values that you can multiply together to get a to the fourth. So I know that that's a squared, because a squared times a squared is a to the fourth, okay? Well, what about b to the fifth? Well, I can have b squared times b squared, but that only makes b to the fourth. I need one more b, okay? And what about c to the sixth? Well, c to the sixth can be, I can have a pair of c to the third times c to the third, right? c to the third times c to the third is c to the sixth, okay? So now that we have everything broken out, we can find the pairs. Here's a pair of 3's, cross one out, set one free. Here's a pair of a squares, cross one out, set one free. Here's a pair of b's, cross one out, set one free. Here's a pair of c's, cross one out, set that one free. Okay, so everything that's outside of the radical sign now is a 3, an a squared, a b squared, a c cubed, and everything that's left over, let's see, we have a 5, we have a b, and I think that's it. Okay, so simplifying this, we have 3a squared, b squared, c to the third, radical 5b. Okay, but remember the very important note that we talked about earlier. Remember this, when the radical expression contains variables, and in this case it does contain variables, we have to make sure that if there's an even exponent inside the radical sign and it simplifies to an odd exponent, we have to add in absolute value bars. So let's see what we need to do. Here are our variables. A to the fourth, we started off with an even, so let's see what we came out with. We came out with an even, so we don't have to worry about that. This one's an odd one, so that's okay, but this is an even one. What did we come out with? We simplified it to be an odd number. So in this case, we have to add the absolute value bars to c to the third to make sure that the value c to the third will be a positive value. Okay, so rewriting this, you'd have 3a squared, b squared, absolute value of c cubed times 5b. Okay, so this will be your simplified answer. Okay, so please give this problem a try. Okay. Okay, next step, when we are simplifying rational expressions, or radical expressions, sorry, you'll also be using a property called the quotient property of square roots. Okay, so this dictates that if you have a fraction as your radicand, you can split it up as the square root of the numerator divided by the square root of the denominator. And again, both a and b are greater than or equal to 0. Okay, you can never have a negative value underneath the radical sign for now. So what does simplified mean? We keep on talking about simplifying these radical expressions, but let's really get into more detail about what it means to be simplified. Okay, so simplified means there are no radicands that have perfect square factors other than 1, which means you've broken the coefficients down and you've broken down the variables so that there aren't any more perfect square factors. Okay. Second thing, the radicands cannot contain fractions. Okay, and that's because the radicands cannot appear in the denominator, and we're going to talk about this in just a second. You notice that in the quotient rule, you can write a fraction as the radicand a over radicand b. Okay, so you can split it up, but this doesn't necessarily mean that it's simplified because, like we said before, radicands, no radicands can appear in the denominator. And here you have a radicand in the denominator. So whenever you see this, you have to rationalize the denominator. Okay, so this means we have to take the problem one step further to simplify it. Okay. So using that property, we are going to simplify this problem right here. Okay. So just like the quotient property said, we can split this up as the square root of 6y divided by the square root of 12. And here is an uh-oh, because what you see is a radicand in the denominator, and we cannot have that. Okay. So we're going to do this procedure called rationalizing the denominator. Okay, and there are two cases. So this is the first case. The first case is when what you have in the denominator as your radicand is a monomial. Okay, so this is case 1. okay? When it's a monomial. What you want to do to simplify this is to multiply by the denominator over the denominator. And the reason why we're doing this is that this is equivalent to 1. We are not changing the value, we're just removing the radical symbols, because radical 12 times radical 12 will give us our pair. Okay? 6 times 12y. Okay? So when we have the pair, just like we said in before, we can kill one off and move one out. Okay? So I'm going to simplify this now, and let's break it down. So you only have 12 in the denominator. There's nothing left and underneath the radical sign. Okay? Square root of 6, we can break that out. 6 is 2 times 3. 12 would be 2 times 2 times 3. Okay, and then you have a y. Okay, so let's find some pairs. Okay, I can use the commutative property. We'll move all the 2's together. We have 3 of them. We've got 2 3's and the y. Okay, so again, we need to identify our pairs, or twins. Here's a twin, killing one off. Setting one free, we will have 2 times 3 times square root of y over 12. And 2 times 3 is 6. And of course, we can factor out, looks like we have common factors. That's 1, that's 2, square root of y over 2. Okay, so what do we have next? Okay, we have case number 2. Okay, I'm going to show you and highlight the difference between case number 1 and case number 2. Okay, case number 2, you have a binomial. Okay, we have a binomial, and we cannot have radicands that contain fractions, and we cannot have radicands in the denominator. And so to rationalize this, what we're going to do is we are going to multiply by the, I'm going to write this, multiply by the conjugate, okay? Conjugate. And the word conjugate is a new vocabulary word. And the conjugate means it's the dots pair. Okay, it's one way to look at it. Okay, move that up. Okay, the dots pair in order to get rid of the radicand. Okay, so what you're going to be multiplying by is the dots pair. Instead of 2 plus the square root of 2, we're going to have 2 minus the square root of 2. Remember, when you factor dots, you'd have 1 plus and 1 minus. Okay, so again, we don't want to change the value of it, we just want to expand it. So we're going to multiply it by our 1. Okay, so let's see what happens when we multiply this. Okay, I'm going to put this down here to give us more room. In the numerator, we can just multiply straight across. And this is, of course, a binomial, so we'll know we'll need to distribute this value. Okay. In the denominator, what we have is 2 times the square root of 2 times 2 minus square root of 2. Okay, so we'll need to FOIL this piece. Okay. When you distribute the numerator, you'll have 6 minus 3 times root 2 all over the first, which is 2 times 2 is 4. Outside, this will be minus 2 times root 2. Inside, plus 2 times radical 2. And the last, minus, now, square root of 2 times square root of 2 is 2. Okay, so just like our dots, the inside, the outside, the inside will cancel out. Okay, so what we're left with, will be 6 minus 3 root 2 all over 4 minus 2. Well, 4 minus 2, we can do that. 4 minus 2 is 2, okay? And we can simplify this even more because we know that we're dividing by monomial. That means we can divide each term by 2. So 6 divided by 2 is 3, and 3 has root 2. Okay, so this will be your most simplified answer. Okay, you don't have any more radicands that have perfect square factors other than 1. There are no radicands that contain factors, and no radicands appear in the denominator. So we are all set to go here. Okay, so again, highlighting the differences. Here you have case 1 where there's a radicand with monomial. Here there's a radicand that's a binomial. Okay, so please use that example to try these two problems, and we will talk about these when you come back to class tomorrow.